Okay, good. Hello, everyone. Welcome to the second day of our QNickel workshop. And there were already some questions about the homeworks and certificates, so I would like to clarify a few parts. So first of all, as we said yesterday, the homeworks will be in Canvas. So I've already sent you invitations to Canvas to the email addresses that you provided during the registration. So please check your email accounts, check your inboxes. Also, sometimes you'll have to check the spam folders because in the past we also had many such situations that the invitations just went directly to spam. And accept the invitations. And after joining Canvas, please set your correct first and last name because this will be the names you will have on your certificates. This is very important. And also you can set your correct email address to which you would like to receive your certificate. And there will be 4 homeworks, 4 quizzes. So I will soon share the screen of Canvas to show you where you should look for the quizzes, because there are 2 different parts. There are assignments and quizzes. So the first quiz will be available today at 7 p.m. Warsaw time, and the deadline is November 5th, so 2 weeks. More than 2 weeks because it will be until the end of day. So you have more than 2 weeks. The second quiz will be available on Tuesday, so at least that's our plan. The third quiz will be available on Saturday, the fourth on Sunday. And yeah, the deadlines, currently all the deadlines are set to November 5th, but of course, we encourage you to do these homeworks earlier. For each quiz, you will have 2 attempts and only the higher score counts. Right, so this is done because we expect that um, when you do something for the first time, you may just make some mistakes and later regret that you just started something earlier. And for each attempt, you will have 30 minutes, right? And in order to get the certificate, you need to obtain at least 50% points from each of these 4 homeworks, 4 quizzes, and at least 70% points from all homeworks together. All right, and now I will stop sharing this slide. So I will later share this slide with you on our Discord. And I will share with you the canvas. So let me do it. Yeah, canvas is here. Okay, hope you can see my screen now. So this is the canvas of our QNickel6 workshop. And here we have the quizzes. So currently, these quizzes are probably not visible for you because they will be available later. So the first quiz about Deutsch algorithm and phase kickback will be available from today at 7 p.m. The second quiz will be available on Tuesday, and the other 2 quizzes on Saturday and Sunday next weekend. There are also some assignments, but we've decided to skip them for this workshop. So you don't have to do these assignments that are here. You just have to work on the quizzes. And there are 4 quizzes. Currently, the deadline for each of them is November 5th. And you will have 2 attempts to approach each quiz and 30 minutes for each of them. I hope it is clear, but it's time for questions. So if there are any questions, just let me know and I will try to answer. This is recorded as well, so the video will be later available on our Discord. So you can watch it later to be sure. But if there are some questions now, I'll be happy to answer, to clarify. Okay, I don't see questions, so I hope that everything is clear. So please check your inbox and join the canvas. I'll now stop sharing. And Justina, If you are ready, the Zoom is yours and we can start the second day session.
Hello, everyone. Can you hear me and see my presentation of QNickel data?
Yes.
Okay, great. So in the agenda for today, we will still continue working on conventional quantum algorithms in Qiskit. I'm planning to explain the Deutsch-Jozsa algorithm and the Bernstein-Vazirani algorithm. In the anticipated agenda, we thought that we will be able to also do the Simon's algorithm, but unfortunately, I don't think that we will be able to do that. So I think we can start with this first algorithm, but before that, I've seen some questions on the Discord channel about the oracle. So what really is an oracle? And that's the thing I didn't say yesterday. So an oracle can be thought of as a non-transparent box that is like placed on a quantum circuit. And we don't know like exactly what is inside this box. So we don't know like which quantum gates are there. But what we can do is to try different inputs to just give different inputs to this black box and observe what is the output. And based on that, we should be able to get some more knowledge about what is inside this non-transparent box. So basically, we know that this implements some kind of function. Usually we know the properties, like we know the properties of the function. So for example, in the Deutsch algorithm that we saw yesterday, we knew that there could be only two types of functions, the constant functions and the balanced functions, and both of these functions were defined for a single. So there was like single binary input and single binary output. And like, so the name oracle refers to these UF that can be seen in quantum circuits. So this is the quantum circuit for the Deutsch algorithm we saw yesterday. For the Deutsch-Jozsa algorithm, we also have this oracle in here. And for the Bernstein-Vazirani algorithm, we have this oracle in here. And what we are trying to do is to basically try all the possible inputs and see and like make some meaningful results out of that. That's why we use the Hadamard gates. And also, like in the case of the Deutsch algorithm or Deutsch-Jozsa, we are using this quantum kickback phenomenon, which we calculated yesterday. So what happens if we have like two registers, but it doesn't matter. So this first register can consist of multiple qubits, and the second register, like, okay, it can be a single qubit, but when we apply this type of oracle that is defined in here, so this operation is just the XOR function. It's basically applying a phase to the first qubit, and the phase is defined as follows. I see that there is some message on chat. Okay. It's not a question. So yesterday I promised that we will go through the calculation of how the Deutsch's algorithm works. And I think it's time we start to do that now, because then we will extend this version to the Deutsch-Jozsa algorithm. So that I've just copied the circuit from the notebook, and now we will try to see how the quantum states behave. So first of all, let's start with this first state. So let's calculate psi 0. And psi0 is very simple because it's just this original state 0, 0. And when I write this state this way, this is the first qubit, and this is the second. So I'm not using the Qiskit convention. Okay, now we can calculate the state psi1. So on the top qubit, there isn't any quantum gate. So we can treat it as an identity gate. So it's, and on the bottom qubit is Adamard gate. So we can calculate it the following way.
Don't you mean a NOT gate?
Oh, yeah, sure. Thank you. That's a typo. Thank you very much. And after that, yeah, it's easy. We can see that it's the state 0, 1. Then we need to actually apply the Adamard gates. So I was ahead of what I wanted to do. So it's Adamard on both of qubits. And it's applied to the state 0, 1. So it will be convenient for us later if I expand it in the following way. So I will apply, okay, so apply H to 0, tensor product H to 1. And the first component I will write as 1 over square root of 2, 0 plus 1. But the second component I will write in the shorter form as the cat minus. So that's the state side 2, and now we will be calculating like the effect of applying oracle. So for that we need to remind ourselves what this oracle does. So I will. So when we apply, maybe I will write it here. So UF applied to some x and minus, it's equal to -1 the power f of x minus. That's what we calculated in the phase kickback notebook. So I will call this equation this asterisk. So now we can try to calculate psi3. So yeah, we just want to apply this formula. So let's write it the following way. So we have this EUF operator, and we apply it to the whole gamma 2. So it's 1 over square root of 2, 0 minus. And then it's plus 1 over square root of 2, 1. Minus. When we have it in the following way, it's easy to apply the blue formula in here because we have this excess present here. So what we actually get is 1 over square root of 2. I'm going to pull it in front of the parentheses, and it should be -1 to the power f of 0. Okay, there's one thing I could have done earlier. Would it be more readable that way? Okay, let's leave it like that. So it's 0 minus plus 1 over square root of 2. No, it's the 1 over square root of 2 is in front, so sorry. I will just erase that. Let's just write that it's -1 to the power f of 1 at 1, and this everything should be multiplied by at minus, because we just no. I'm trying to do too many things at the same time, but this should look correct now. So that's the formula. So what we just did is that we applied this UF to the state that we had. So actually we got two x's, one of them was 0 and the other was 1. So that's what we done. I can't erase it. So now we know that when we want, so that's gamma 3. So yeah, let's erase that. Oh, cool, it works now. Sorry for that. I have some troubles with my virtual whiteboard. Yeah, so we calculated this psi3. So what we want to do now is to calculate psi4. And we see that in psi4, we don't really care about the bottom qubit. So we just want to apply Adamard gate on the top qubit and then measure it. So we can write this state psi4 as psi4 0, because it's not the whole psi, but it's just the top qubit. So basically we are just focusing on this part of the psi3 that is from here. And the minus state, like it doesn't change anything for us. So let's finally calculate psi4. Yeah. So to calculate that, we just need to apply the Adamard gate to everything. So it's 1 over square root of 1, and we can try to like calculate that. So let's see, it should be 1 over square root of 2 minus 1 f to the power of f of 0, and then Adamard is applied to 0, so it should be 1 over square root of 2, 0 plus 1, and then we add this second part, so it's minus 1 to the power f of 1, 1 over square root of 2, 0 minus 1, because we are just applying this Adamard gate first to 0 and then to 1. Okay, and let's try to expand that. So, so what we have in total, it will be 1 over 2, because we can multiply all of that. Okay, and now let's take a look at the coefficients. So first of all, what is in front of the cat? 0. So it will be plus. So it's minus 1 to the power f of 0 plus minus 1 to the power f of 1. That's 0. And the second part, okay, I don't have enough space in here, so let me copy it and we will go to the next page. Okay. Maybe you can see both of the pages at the same time. Okay. Yes. So now I can continue what was in here. So let's just write plus. And the second part will be on the second page. So near the cat 1, what we have is, right? So, oh, sorry. Let's highlight cat 1. So that was the part related to cat 0. And now the part related to cat 1 is -1 to the power f of 0 minus, and this minus comes from here, minus 1 to the power f of 1. That's in a bracket, not a bracket, in a braces. And then the state is 1. So that's the whole formula. So it's 1/2. This is the coefficient before the cat 0, and this is the coefficient before cat 1. I'm checking the chat, no questions. So now we just need to think about the functions that we have. So the function that we have, there are like two options. So the first option is that f is constant, which means that f of 0 equals to f of 1. So the formula isn't big, so just calculate the, like, what's the actual value of these coefficients. So for cat 0, let's assume like there are two options. So the first option is that f of 0 equals f of 1 equals 0. So it will be -1 to the power of 0 plus -1 to the power of 0, which will be 2. And if f of 0 is equal to f of 1 and equal to 1, it will be -1 to the power of 1 plus -1 to the power of 1, which is -2. And what does it mean? So that's the coefficient that it's in front of the cat 0. So what we can, and we can't forget about the fact that it's 1/2. So it's like actually, so yeah, the coefficient before cat 0 is the amplitude. So it's 1/2, either 2 or 1/2 minus 2. So that's the amplitude. And the probability for getting some state is the amplitude squared. So that's 1 and that's 1. So the probability for like measuring state 0 is 1 when the function is constant. So we checked both of the options. If f0 equals f of 1, then this first term that is visible in here equals to 1. This second term related to cat 1 should equal to 0 because the probabilities should sum up to 1. So we can quickly check that if we have, so this will be the coefficients for the cat 1 when a function is a constant. So it will be either -1 to the power of 0 minus -1 to the power of 0, or -1 to the power of 1 minus -1 to the power of 1. So it's 0, 1 minus 1 is 0, and -1 plus 1 is 0. So the probability of getting the state 1 when the function is constant is 0. But we can also think about the version in which the function is balanced. So if f is balanced, then the coefficients for the state 0, I take them from here. So I will just write them quickly. So it's -1 to the power f of 0 plus -1 to the power f of 1. So this should be either -1 to the power of 0 plus -1 to the power of 1. So it's so it's 0 minus 1. No, 1 minus 1, which is 0. And yeah, the other way around, it will be the same. It will be -1 plus 1. So we won't calculate that, but so that's the amplitude. Amplitude squared is still 0. So let's just calculate the amplitude and then probability for this this cat1 state. So it was -1 to the power of 0 minus -1 for f of 1. So the two possibilities, that's -1 to the power of 0 minus -1 to the power of 1, which is 2. Or it could be -1 to the power of 1 minus -1 to the power of 0, which is -2. So that's the amplitude amplitudes we can expect, but there is 1/2 in front of the whole formula. So the probability of measuring the state 1 is actually 1/2. Yeah. So 1/2 times 2 squared, which is or 1/2 times -2 squared. Both of them are equal to 1. So it means that if the function is balanced with the probability equal to 1, we will measure in this first qubit state 1. Yeah. Are there any questions to that? I will check chat. Can we write H01 as plus minus? Yes, we can. That will be very compact, but in this case, it was easier for us to actually write it the way I wrote it, because then it's easy to see how let me write it, how this oracle function works. So yeah. Any other questions? Okay, so that was all for the Deutsch algorithm. So now we will focus on the Deutsch-Jose algorithm, which is, like, as you can see, the quantum circuit looks kind of similar. The only difference is that the first register can have multiple qubits, and we so let's come to the definition. And I haven't said it yesterday, but the functions we are considering, they are not really meaningful. Like, they are just toy problems which enable us to see, like, why the quantum computing can have some, can bring some speed up. So the function for the Deutsch problem is that we as input we can have either 0 or 1, and the output will be 0 or 1. So it's 1 bit as input and 1 bit as output. In the Deutsch-Jose, we can it could be n bits, so it will be an n-bit string of zeros and ones, and it's mapped to a single value, 0 or 1. So yeah, and in this case, we will also talk about constant and balanced functions, but we will define, so yeah, we'll define them exactly the way we defined them yesterday. So a function is constant if, regardless of what is the input, as output, we always get zeros. And the function is balanced if it maps exactly half of the bit strings to 0 and the other half to 1. So in here we have an example of a balanced function. So for the inputs 0, 0 and 1, 1, the output is 0. And for the functions, the inputs 0, 1 and 1, 0, the output is 1, 1. So that's this is a balanced function because half of the input output is 0 and half is 1. This is constant because it's all zeros. Another constant function would be all ones. Okay, so the formal definition of the problem is that we are given a binary string and that is mapped to 0 or 1, and this 0 or 1 tells us whether the function of this binary string is constant. The case of it is constant when all of the outputs are the same, or balanced if it's not. So the input size changes, but the oracle is the same. So that's the same we saw for the Deutsch problem, because Deutsch is just an extension to the Deutsch problem. And when we see QNickel6, now it's not a single binary value, it's an n-bit. So yeah, we just need n qubits to represent this x. So it's a vector. Yeah, x is a vector now, like of n x's. Okay. And when we will be applying this, this UF, which is the oracle, the phase kickback still applies. So it will work the same way it worked before. Here we have a reminder about notation. So maybe I will write it down. So the thing is that when we write, for example, when we write something like this, so when we use this notation, what we really mean is that, so it can be interpreted. So in here, n is 3, and it's just applying Hadamard gate to all of the qubits that were instantiated in the state 0. So that's just a fancy notation. And we will talk a little bit more about the Hadamard gate because it will be very important for us. And then there will be a task for you to calculate something using pen and paper. But let's still focus on what we need to learn before we continue. So let's talk for a bit about the Hadamard gate. So so you know that Hadamard applied to 0 is 1 over square root of 2, 0 plus 1. And Hadamard applied to 1 is 1 over square root of 2, 0 minus 1. So now, so we see that the only difference between these two states is the sign here. So it can be convenient to have like to have a notation that will help us to express this state regardless of whether it's 0 or 1. So for now, maybe we should write this like x1, because this x is not this full vector of size n, it's just a single x. So that's a single binary value. So let's write this like 1 over square root of 2 cut 0 plus minus 1 to the power x1 1. And now it's not hard to understand that it works correctly, because if we have x1 equal to 0, so it's Hadamard applied to 0, then this will be 1, which will leave this plus here. But if we have this x1 equal to 1, then this minus 1 to the power of 1 is minus 1. So instead of plus here, we will have a minus, and this will be correct with in accordance with this formula. So in that way, we can like try to write it even in a more compact manner. So the first thing we can notice, so we are just trying to think about a formula in which we can use some, we want to make it as compact and generic as possible. So the first thing we can try to do is to like write it the way it is written now. So this is 1 times x1. And in like when we have 0, it can be so let me rewrite it. I don't have enough space. Yeah, so we can write it as in here the power can be 0 times x1, because it's still to the power no, not here. Yeah, so let's write it like minus 1 to the power 0 times x1 at 0, because it will always give us 1. And we have something similar in here. And if you want to have it in a compact way, we can write it as a sum over some binary variable. So it will be minus 1 to the power of z at z. So yeah, that's this is the representation. So this is the compact representation of what Hadamard gate. So it's like this simple version of Hadamard gate does to some single qubit state. And we, instead of writing it as a sum of like some different things, we are just using one variable to represent that, and it seems to work, because if that's basically a sum in which this first coefficient will be 1 and cat 0, and then based and this other one will be the one that is related to I'm missing x in here, sorry. Yeah, to the effect of a multiplication. So based on so in the first case it's x1 times 0, and in the second it's x1 times 1. So based on the sign of x1, like either it's 0 or 1, so this minus 1 to the power of x1 in the case of I'm not sure if I explained it in a way that like everybody can understand it, but the main thing is that Adamart applied to some arbitrary state can be expressed as such a sum. And if somebody needed to like think about it for a while, it's also written in here. And now we would like to understand this Adamart gate on an n-qubit register. So I will maybe write it in here. Okay. So if you have an n-qubit register, so it's this Adamart. So at first, let's focus on a register with zeros only. So like that's oh sorry, I wanted to highlight, erase. So that's like this case. We can write it as 1/2 to the power of n. I will write it and then I will explain it. Sum of all x's of the combinations to the power of n. So yeah, now it's not related to the thing I wrote in here, not yet, but so let's imagine we have a quantum register like I've shown in here, and you just want to apply an equal superposition. So you are using Adamart gates. So the state can be, so this state can be represented. So for example, for these 3 qubits, it will be 1/, so it's 3 qubits, so it's 2 to the power of 3. 3 qubits, 8 states. Yeah, it should work. And all the possible values are 0, 0, 0, plus 0, 0, 1, plus etc., plus 1, 1, 1. So in fact, this can be also written in another form. So more compact form. We don't need to always use the binary form. Binary form, by binary form, like I mean using only zeros and ones. We can write it also as 0 plus 1 plus, this will be 2 plus 7. We can use this integer representation, and then we just know that underneath it's binary, but it's like more compact. And in the notebooks in here and in the homework, I think there is one task in which they use this integer representation, but they are equivalent. So this can be also written as 1/√2 to the power of n, and then we have sum, and it's from x equal to 0, 2 to the power of n minus 1, because we have, that's the number of states we have. And then this, maybe I won't. So, and this will be like this. So that's a different, so that's different ways in which we can write an equal superposition. Like either it's just a sum of all the possible combinations in the binary form or in the integer form. I will stick to the first one, but they are the same option. You just need to convert one to like it's easy to convert one to the another. But enough about that. We just want to be able to apply Adamart gate to an arbitrary state. So so for a second we were talking about how to apply Adamart to the state 0, which is an equals superposition. But yeah, state 0 is a very nice state, but sometimes we want to have some different states than all zeros. So how to apply Adamart gate when the state is different? So let us define a few vectors. So we will have vector x, and this consists of x1 till xn, so the length is n. Then we have vector z, and it's z1 to zn, and this z actually comes from the thing I was writing in here. So I will leave these two tables side by side because we will be able, so we know how this Adamart gate acts on a single x1, but we want to know how it behaves when it's applied to the whole vector. So yeah, let's calculate that. Oh, we need one more thing. So because in here we have like a simple multiplication x1 times z, because there was only one z. So in here I will write it as z1. But like how to calculate how to calculate something like this. And here we are not calculating. Okay, so how to calculate this multiplication? So the vector, so the elements of a vector x times the elements of a vector z, and we call it bitwise end operation modulo 2. So that's the thing that we will need. It will be useful in, like, we will see why it's useful in a second. So just see how it's defined. So it's x1 times z1 plus x2 times z2 and plus xn times zn modulo 2. And like in a compact form, it can be written as sum from I equal to 1 xi z I modulo. So we just know how to calculate this multiplication. So from this example, we see that it will be needed. And yeah, basically when we try to apply the Adamart gate on multiple qubits, when the state is not 0, it's some arbitrary state, we can just use this formula. So let's see how it should work. So the first component would be 1 over square root of 2. Then is this sum. It will be z1, which is in the set 0, 1, and it's minus 1 to the power x1 times z1, and the state in here is z1. So that's the Adamart gate applied to the first qubit, which is x1. Then the next component is 1 over square root of 2. Sum, it will be z2 that belongs to 0, 1 minus 1. It's actually x2 z2, and the state is z2 because we take it from here, and then there will be some more, and the last one will be 1 over square root of 2 sum zn, which is also 0, 1 minus 1 to the power xn zn and the state is Zn. So so what we can see here is just some explanation on how to apply the Adamart gate on some arbitrary state. And we have task number here and number 1 here, which is to apply Adamart gate that uses 4 qubits to the state 15. So now it's the time for you to solve this task, and the hint will be like that the state 15 is the same as 111, because they prefer to use the integer form, and I will be explaining everything today using the binary form. So for the people who were not present yesterday, we have on the Discord channel, we have a channel called Workshops, in which I write what tasks are to be performed, and then you can use the emoticons to log your activity. The first one is to show that you're working on this task, that you've finished. It's the second, and that you need more time. And now we will have around, I think, 4 minutes to finish this task number 1. So it's notebook 804, and the task is task number 1, and then we will do it together. I can see that people are still working on this task, and it's an important one to get, so maybe a minute and a half more. Okay, it seems that all the people voted that they finished this task, so we'll stop the timer now and let's do it quickly together so as to be on the same page with the understanding of this task. So yeah, we will be using this formula we've just derived. So it will be 1 over square root of 2. It's sum z1 0 1 minus 1 to the power z1 and x1 is 1. So we leave that right for now. Yeah, and we can write it 3 more times. Okay, so when we do that, and I will just add the tensor multiplication in here because we are missing that, and change the indexes for proper ones. So it should be z1, z2 times 1, z3 times 1 because we have this x1 here, and z4 times 1, and we just change the indices. So now this is how we can write it using this, maybe using the formula from the previous slide. So when we have all of that, we can see that, for example, like just take a look at the first braces. So it's 1 over square root over 2, and we have, so it will be minus 1 to the power z1, which is 0 times 1, and get 0, and it's plus minus 1 to the power z1, which is 1 times 1, and the cut is 1. This will look the same. This will look the same for the rest of the things in the parentheses. Yeah, so exactly, we just want to have this same thing 3 more times. So actually, we will see that it's 1 over square root of 2, 0 minus 1, tensor product 1 square root over 2, that's 0 minus cut 1, 1 square root over 2, 0 minus 1. So basically it works the way we would expect that it works. We just have a very nice compact form in which we can write this this formula, and I haven't written how this compact formula works. So in general, you can write, or maybe I will write it in here, that when you have Hadamard applied to n qubits and the state is like some arbitrary state, it's 1 over square root 2 to the power of n, because we are multiplying this 1 over square root of 2 like that n times, and this is the sum z is equal, it's 0, 1 to the power of n minus 1. This is this multiplication I mentioned. So this is this multiplication I've just written is defined in here. And the state will be z. So this is what was to be done in the task number 1. Are there any questions to that? I can't see any on chat, so I think we can move further with this notebook. So there is, we will skip task number 2. In task number 3, so there is a question. So the first question is, how many times do we need to use the oracle f if we want to solve this problem classically in the worst case? And I will give you a few seconds to think about that, and I will tell you what is the solution. So in general, in this Deutsch-Jozsa problem, we have constant functions and balanced functions. So in the case of constant functions, we will always get the same output regardless of what's in the input. And in the balanced case, there will be half of zeros as output and half of ones as output. So how many different inputs to this function are possible? So maybe I will write it. So when we have this function, it's a map from 0, 1. So the input consists of 2 to the power of n strings. Like yeah, because when we have, like, for example, 0, 1, so that was the case for the Deutsch algorithm. Yeah, okay, so sorry. So what I want to say in here is that let's assume that that we have 2 bits. So the input could be 0, 0, 0, 1, 1, 0, and 1, 1. So 2 to the power of 2 is 4, but oh yeah, I know how I can explain that. So let's assume that we have these 2 functions. And let's see at this, sorry, you can't see that actually now. I will resize it. And let's see at the example of the balanced function. So we are just trying to get some more information about what's inside our oracle, whether this function is constant or balanced, and so there are 4 possible inputs we can try. So at first we've tried this first one, and we got the output 0. Then we we checked this input 1, 1, and we also get the output 0. So we can think, okay, so maybe since we've received 2 zeros, so like we know that half. So it can, in this moment, it can either be a constant or balanced function, because the knowledge we have like no knowledge about what's else, because we know only we have knowledge about only the things we've asked about. So we can hope that that this might be a constant function because it's 0, 0. So now we are just trying a different input. So maybe just try this input, and we see, oh, it's a 1. So if we are unlucky, when we need to ask 2 to the power of n over 2 minus 1 times. And why is that? Because in the case of balanced functions, the output 0 is like 50% of time. Like it's 50% of all outputs. It's not a probabilistic result, but yeah, and like the other half is ones. And we can try the inputs for which we get the same output. And we might think that this is a constant function, but when we actually try like half of the possible input combinations, we need to try one, okay, plus 1.
So the power should be n minus 1 and not n over 2.
Exactly. Thank you. That's my mistake. Thank you for this correction. Yeah, I think it looks better. Yeah, because I like, okay, that's what can be written in here. So we need to try half of all the possible inputs plus 1 more. And so are there any questions regarding that? Okay, there is something on chat. So the first question for the last task, set I is a vector state or is a operator. Okay, so it's a vector state. What happens if the function outputs 175% of the time, like, or so in here we are just considering by the definition of the balanced functions, we are considering only the functions in which zeros and ones like so half of the possible outputs are zeros and half are ones. We can't consider a function like or in here. I hope this answers your question. Yeah, so that was the first question of the discussion, and the second question is how many times do you think we will use the Oracle F while solving it with a quantum computer? So maybe you can guess on chat how many times we will question the Oracle. Okay, so the answer is only 1 time, so we can see the exponential speed up in here. So in the case of the Deutsch algorithm, the speed up was like 2 times because normally we will need to check the input 2 times, but we needed to do it only once. And here it will be, we need to check it just once. So the speed up is exponential. So the plan for this notebook is that we will go through the analysis of this circuit, so why it actually works, and then there will be time to implement this this algorithm and check how it works. So let's start with the analysis. It will be somehow similar to the one we had for the Deutsch-Jose, because it's a similar algorithm, but we will have like a bigger first register. So I will copy the circuit, and let's analyze every state. So size 0 is easy because it's just state 0 on n qubits. Because okay, so x has n qubits. And we have one additional qubit. So this is like data qubits, and this is the target qubit. So we know what is the state gamma 0. Then in the state gamma 1, we don't change the data qubits. The only qubit that is changed is the target qubit, and it changes to state 1. And now we will have the Hadamard transfer of that. So that's when the things we've just learned will become useful. So psi 2 is Hadamard gate on n qubits applied to the state 0 on n qubits, and we are applying also this Hadamard gate on the state 1. Okay, and we've seen a formula for how to calculate that. I think it's in here. So it's just a superposition of all the possible input states. So let's write it this way. So it's 1 over square root 2 to the power of n sum. So maybe it will be x 0, 1 to the power of n. So that's an equal superposition, and we will leave and this. So we applied Hadamard to this qubit in state 1, which is ket minus, and we can leave it like that. And now in psi 3, we will observe the phase kickback. So maybe I will write this formula once more for the phase kickback. So let me write it quickly. So with this, so UF applied to x minus is equal to -1 to the power of x minus. So it's phase kickback. So let's try to. So we see that this is exactly in the form in which we needed, because we have x state and minus is the last one. So let's actually calculate that. So we will have 1 over square root 2 to the power of n sum over x, and we will just have this -1 to the power f of x times x, and tensor product with this minus state. And from now on, when we will be calculating psi 4, which is actually applying Hadamard gates to psi 3, we won't care about the target qubit. So we can write this state gamma for also 0, because when I showed it for the Deutsch problem, I wrote it as a 0. So 0 is like this 0th register for data qubits. And before we calculate that, I will write once more the formula we've just derived for applying Adamart gate to an arbitrary state when it's like an n-qubit state. So it's 1 over square root of 2 to the power of 9. N, not 9. We have some binary variable. Z, it's not a variable, it's also a vector. -1 x times z. It's this bitwise multiplication. So yeah, that's this one, x1 times z1 plus something plus xn times zn modulo 2. And we just need the state at the end. So sorry. So I will write it. Okay, so that's just the formula, and we need to apply it, and we will focus only on this first part because that's where the Adamart gates are applied. So let's try to write that. Okay. So I'm writing down the thing that is in yellow right now. So it's 2 to the power of n sum x belongs to. So it's a n-qubit vector, and it's minus, so it's from phase kickback. But now we need to apply Adamart gate to this x. So we use this blue formula, so it's 1 over 2 to the power of n sum z 0, 1 to the power of n -1 x times z cat z, and we can a little bit simplify that. So it's 1 over 2 to the power of n, because that got simplified. And now we have the sums. So they are sums over very similar terms, so we can write it as like one sum. So like, okay, maybe I will write this as like 2 sums. Okay, it doesn't matter. So yeah, I can write it. So it's a sum over x over z, and now we will have -1 to the power f of x times -1 to the power x times z at z. But this can be simplified. So if it's multiplication, we can add the powers. And that's the state for 0. So yeah, we are actually, so now we need to measure this state, and so here we need to like analyze like possible values, and we know that in the case of the Deutsch algorithm for constant functions, the output was always 0. So let's just make an analysis of what happens if we measure a state that is all zeros. So now, okay. So now we are analyzing the possible Z. And we are starting with Z equal to 1. Like we need to start somewhere, and we just want to observe what happens if maybe I will show two of the slides. If the Z in here, so this whole vector, so we are just getting rid of this sum. We will just have so that's the amplitude for the state 0, 0, 0, 0. How many zeros we want to have, and so maybe I will write this down. So the amplitude for the state 0 applied to n qubits is 1/2 to the power of n sum whatever the input x is, so all possible combinations -1, and I will write this down, f of x. But we can do some simplifications in here, because when we know that Z is all zeros, we can calculate x times Z, because whatever it is, so whatever x is, it's like x1 times z. Okay, it's not a vector, it's just the value, plus x2 times 0 plus, so we are doing this bitwise AND operation, modulo 2, and we'll have xn times 0, because in Z, so Z1 is 0, Z2 is 0, Zn is 0. The result of this operation is 0. So actually the thing we wrote can be simplified. Okay, and it can be written as, so x times Z is 0 now, and that's the amplitude for the state all zeros. So let's analyze it. Because now this amplitude depends only on the value of the functions. So the first case would be constant functions. So how does this amplitude behave for constant functions? So let's take a look at constant 0. And so in constant 0, it will be 1/2 to the power of n sum. For all inputs, it will be -1 to the power of 0. So we will actually have, so this will be 2 to the power of n, this sum, because we can write it in another form as sum x equal from 0 to 2 to the power of n -1. So that's 2n terms, and it's we are just summing 1 to n times, and we are dividing in it by to the power of 1. So that's the amplitude. So the probability is the amplitude squared, which is 1. And constant 0 now. So it's 1 over 2 to the power of n, some x 0, 1 to the power of n, minus 1 to the power of 1. So this will be minus 2 to the power of n divided by 2 to the power of n, which is minus 1. So the probability will be minus 1 squared, which is 1. So it means, so it wasn't an accident that I chose this vector all zeros for this computation, because it turns out that when the output from this algorithm is all zeros, so when we measure all zeros, then we have a constant function. We don't really care whether it's like constant 0 or constant 1, so whether all the outputs are 0 or 1. We just know that that this function is constant when the output is all 0. So otherwise, when we measure, with probability equal to 1, when we measure zeros, the function is constant. So it can be proven that if we measure something else, so if there is at least 1 in this measurement output, it means that the function is balanced. So only if the outputs are all zeros, the function in the oracle, so this mysterious function, was balanced. But if we get any one in the output, it was okay, I might have said balance, but no. If we have all zeros, it's constant. But if we have some 1 in the solutions, then it means that the function is balanced. Are there any questions to that? Okay, I can't see any. So now it's time for you to do the task number 4. So you are given an oracle as you were given yesterday. So it's like external code, and it returns a random circuit with n+1 qubits. This +1 is because we need this target qubit, and there is some kind of oracle. It's a typo in here. So assume that that you need 4 qubits for you need 4 qubits for this data qubits and 1 qubit for the oracle, and just implement this algorithm. So apply the proper gates and see what you can get there. Okay, and I think that 10 minutes are enough for this task. So let's see in 10 minutes. Okay, it seems that the majority of people have finished. So let's quickly see the code. Yeah, so first of all, we need to apply the X gate on the fourth qubit because qubits start from 0, so fourth qubit will be actually the fifth in here. Then we need to apply the Hadamard gate on all qubits. So we can write it as the range. Then so after the Hadamard qubits, we need to compose into the circuit the oracle that is written as an external code. So there is a method to do that. We are composing this oracle that is designed for 4 qubits, and we are just appending it at the end of our circuit as of now. Then we need to have another layer of Hadamard gates. So we'll just change the range because we don't really care about the last qubit right now. And what we need to do here is just to draw the circuit. Oh, we already have that. No, we don't need to draw, we need to measure it. So we measure I will say that in a second. So we measure all the first 4 qubits into a classical register containing of 4 classical values. Yes. So I have some issues with that. Have I imported everything correctly? Let me see. It's weird. Really? Okay, so I've corrected it, but I shouldn't have. So it's like Oracle Deutsch Josa probably. And yeah, so maybe I can have a barrier. So we have on the last qubit, we have the X gate and we have the layer of Hadamard gate. Between the barriers, there is the oracle. We don't know. In here, we can see it because that's the way it's implemented, but in reality, we can't. And then we apply the Hadamard gate and measure the result. So the value in here is 0, 0, 0, 0. It was measured 10,000 times, and the so it means that this function is constant, and it looks like a constant function. Let's try a different one. This should be balanced because there is a CNOT. And yes, the measured string is 0, 1, 0, 0, which means that the oracle was constant. Yeah. So basically that's how it works. And now I think it's time for a break. So let's meet at 5 and then we will continue our work. Sorry, I didn't ask if you have any questions, but if you have, we can do them either now or after the break, maybe after the break, because I already said that there is a break now. Okay, the break has come to an end. I hope you are still with me. So now, do you have any questions regarding the task number 4? Okay, I can't see any. So now there will be some time to solve task number 5. I think that around 10 minutes should be okay. Okay, the time is up, so I will try to like show you some option of what you could have implemented. I will start with the constant oracle. So let's see what I have in here. I proposed an oracle that consists only of the identity gates, and I will explain why is that. So yeah, so I know that we are talking about n-qubit case. In here we had 5 qubits, but it's simpler to explain everything on a smaller number of qubits. So for now we will use 2 qubits, but it can be easily extended to like a bigger case. So we have 2 qubit input, so 3 qubits in total when we have this additional target qubit. So regardless of what is the input data, we have all the options in here. We want to have the output 0. So let's for now forget about like what's going on in these 2 wires, because the input could be either 0 or 1. But on the bottom qubit, we always want to have the output that is defined in this way. So that's the formula. It's whatever the A is the state of the bottom qubit. So this takes state of the bottom qubit and XOR it with the value of the function you have. So when we have it's A XORed with f of x is 0 for all x. So it's just state A. So this implements as the constant 0 oracle. We just don't need any gates. We could have, if we wanted to have like constant 1 oracle, we would just need to add an x gate in here. So still it is like regardless of the number of qubits we have. Then we have I XORed with f of x. F of x is 1, and we always want to have like the negated value of the original state that was on the target qubit. And in the case of the balanced functions, so we also have 3 qubits. And I said that if the top qubit is in the state 1, then change the state of the bottom qubit, and it makes sense to implement it in this way, because if so it's a balanced function, because like half of the inputs output is 0 and half is 1, and when we want to calculate that, so assume that there was some A in here, and the output in here would be A XORed with the value of whatever it is. So if it is 1, and if there in this fx, if there is 1 on the first position, then the value is 1. So in here, if f of x is equal to 1, then on the first qubit, it is also 1. So this state A will be negated. So it will be A XORed with 1. And if we have 0 on the top qubit, then nothing will happen. So it will happen. So it's XOR with 0. So the state will be A. So that will be the oracle for like checking whether the first number is 1. We can also check whether maybe the second number is 1. So when we have everything turned around, we would have it like that. So we can have some other wires in between. So basically, it doesn't matter how many wires we have, we just need to analyze how this function behaves with this, so that how the target QBD behaves with this XOR, and if these things in here implement that. So basically, so for the first version of what I've shown you, we can have a balanced function that contains a controlled X. I will show that. So we have a controlled X on the first qubit. So this is oracle for half of the functions will have one on the first qubit, and the output should be 1, and the other half will have 0 on the first qubit, and the output should be 0. But you could have like any other oracles you wanted to try. So do you have any questions to that? Okay, I'm checking the chat. No. Okay, so now it's time for notebook A05, Bernstein Vazirani algorithm. Okay, so we will use the whiteboard once again. So let me open it. So maybe just first of all, take a look at what is in this notebook. So this is another oracular algorithm. So we will see that there is some magical function that we don't know, and we just want to like kind of guess what's inside. And before we start with the definition of the problem, we would need some notation preliminaries. So the first thing, so it's Bernstein Vazirani. Okay, so we would like to be able to multiply two strings by themselves. So x is like some string of zeros and ones, like that, and s is also a string of zeros and ones. And we want to be able to calculate their product, and this product is defined. So I've shown it in some previous, when I was explaining about the Hadamard gate, but how is this calculated? So it's x1 times x1 times s1 plus x2 times s2 plus something plus Sn, and no, it should be xn Sn, and we take modulo 2 of that. So it's this x I s I. So this will be needed in the definition of the Bernstein Vazirani problem. And in here we have the formal definition. So we are given an oracle function that takes like a binary string consisting of, so it will be n bits and returns 0 or 1. So it maps multiple bits to just a single binary value. And the oracle function is defined as follows. So we have some vector x and some vector s. And s is the secret string. So the length of the vector x and vector s are the same. So it's the length of n, and we can calculate their product. So yeah, at the end we will get either 0 or 1, because the definition of the product has this modulo 2. And like the issue in here is that you want to find out what actually the value of the s is of this secret sequence of bits. So yeah, you can think about this as like some kind of a mask. But we will see in a second how this works, because like seeing how it works on an example, I think will help us. And like they also say in here that this problem is not a real problem, like not a real life problem. It just will show us that there is some power in quantum computing, and that this algorithm, the quantum version of this algorithm, is faster than the classical version. So without further ado, let's see this example, and then we will try to think about something more. So in here we have an example of function f. So this function f is defined for a 2-bit input. So the input is 0, 0, 0, 1, 1, 0, 1, 1. So that's all the 4 possibilities. And we know what is the value for 0, 0 multiplied with this secret string. So when we take 0, 0 and multiply with secret string, we'll get 0. When we have 0, 1 multiplied by this secret string, we get 1. 1, 0 multiplied by this string is 0, and 1, 1 multiplied by this secret string is 1. And the question here is, okay, so what's the secret string? In here, we have the answer given to us. So the secret string is 0, 1, and we can see if it works. So when we have f of 0, 0, it's first input, so it's 0 times 0, which is 0, and then it's 0 times 1, which is 0. So the total output of this function is 0. Then when we have function 0, 1, so the first input 0 times 0 is okay. Here is, I think, a mistake. It should be 0 times 0. 0 times 0 is 0, and 1 times 1 is 1. So the output is 1. The thing written in here is incorrect. For the input 1, 0, we take 1 multiplied by 0, which is 0, and then 0 multiplied by 1 is 0. And for the input 1, 1, we take 1 multiplied by 0, which is 0, and 1 multiplied by 1, which is 1. And then the output is 1. So, oh yeah, I see. Okay, so sorry. The everything in here is correct. They just wrote it like, okay, so yeah, I will explain myself so we know that as is. Sorry. Okay. Oh no. 1 second. Okay. So if they have this defined this way, so the first thing in here, it's so x is 0, 0, s is 0, 1, because like the secret string, okay, they did it that way. So the secret string is in blue. Okay, and when we want to multiply x by s, it's okay, it's 0, 0 times 0, 1. So it's 0, 0 plus 0, 1. And it's 1 modulo 2. No, it's 0, of course. But yeah, the notation is correct. I just misunderstood that. So yeah, you just need to multiply that, and I think you more or less know how it works. And now we see that the new unitary operator. So UF, the input register of n qubits, remains unchanged after this unitary operation. and we have the output register, which is XORed with f of x, and this f of x in our case is defined as this multiplication. And the first question is, using how many queries can you solve some problem, like some kind of this problem classically, and how many queries if you okay, so let's just focus maybe on this classical version, like the deterministic one. Yeah, so let's come up with let's see how this function works. Can we see that on the first level? So in here we had n equal to 2 in this previous example. So maybe we can do that once more. So an important thing is to check what is the value of the following string. So I would say that in a second, why it's important, the following two strings. So the first one will be 0, 1, and the second will 1, 1, 0, and the second will be 0, 1. So it's 1, 0 multiplied by s, and the second one is 0, 1 multiplied by s. So in the first case, you have 1 times s1 plus 0 times s2. And in the second case, you have 0 times s1 plus 1 times s2. So at the end, what you get is the value of s1 and s2. So in the case of 2-bit input, we need to make 2 queries because we just want to like check where the like what's the value of the s, and we are just using like a binary mask. So it will be more visible for a bigger problem. So assume that n is equal to 4. And then we will need to check the following inputs to the following output to the following inputs. So let me write it. So in the first case, it will be 1 times s1, and it will be plus, but all other things will be multiplied by 0. So it will be 0 s2 plus 0 s3 plus 0 s4. In the second case, it will be 0 times s1 plus 1 s2 0 s3 plus 0 s4. So at the end, you see that we get the secret string 1 bit by 1 bit. So that's the way in which we can do this classically. So in the case of n equal to 4, we needed 4 queries. In the case of n equal to 2, we needed 2 queries. So in the general case, we need to have an n bit mask, and we need to like n 1 bit like 1 hot and encoded masks, and ask this question n times. And in this way, we will get what's the secret string. And in the case of these quantum version, so the answer to the first question is n times. And how many queries do you think we need to make if we are to solve this problem with a quantum computer? So the answer again will be 1 query. And the task number 2 is what can we say about the function f? If s is 0, is a vector 0. So let's take a look. So what will be different is that maybe it's okay to see both of them. Okay, so the multiplication, so for whatever the function whatever the input is, it will be x1 times 0 plus x2 times 0, etc. So the output, this function will be 0, so f of x always will be, so for every x, f of x will be equal to 0 if the secret string is 0. So if you see a function, like, for example, like, okay, you had some function in here. If we had zeros everywhere instead of these ones, we would know that the secret string was all zeros. And now this will be the part in which I will explain how this algorithm works. So I will write the mathematical. So in the mathematical way, how the states change, and then you will implement the circuit. So let's start with the analysis of this algorithm. So once more, let me copy the circuit, and we will analyze each state step by step. So before I begin, I will write three things actually, that will be useful. Let me move this circuit, so I will prepare space for that. So the first thing is that when we have, so it's describing the behavior of the oracle. So if we have the oracle UF applied to the state x and minus, so that's the thing you've seen many times today. It is equal to minus 1 to the power f of x minus, so it's just phase kickback, the definition of the string multiplication, so it's x1, sorry, it keeps disappearing, x1 times s1 plus x2 times s2 plus xn sn, and it's addition module 2, and the last thing is the Adamard gate applied to some arbitrary state. So we know it's 1 over square root of 2 to the power of n sum over z strings. Oh, sorry. And it's minus 1 to the power of x times z. And it's like this multiplication with the same multiplication as with z. So now let's focus on actually calculating what are the states. So the first state, yeah, I haven't mentioned that. I should have. And the thing is, sorry, so the thing I didn't say is that we have the same circuit as Deutsch Josa, so Bernstein-Vazirani algorithm has the same circuit form. So the only thing that will change is the function we are analyzing. So this will be just a recap of what we've seen today. So like at some point the things will be different, but for now it's all up until the oracle, everything is the same. So the states say 0 is 0 on n qubits, and this is like this plus 1, 0 on n qubits, and 0 on the last qubit. Then we have state psi 1, which is 0 or on n qubits, and then the last qubit is inverted by the poly X gate. Then we apply the Hadamard transform. So it's side 2. So we are applying this Hadamard gate to the state 0 tensored with 1, and it for sure has been seen today, but maybe I will write it down also here that Hadamard gate applied to 0 is 1 over square root 2 to the power of n, sum over every x, so every possible state. Yes, because like every possible input is equally probable. So let's write that. So the first part is 1 over square root 2 to the power of n, sum for all possible inputs, and then we multiply by the Hadamard gate applied to 1, which is the minus state, and we always write it in the following form because it's easy to apply the formula for the oracle. So, and the phase kickback later. And from now on, we see, so we can calculate actually, yeah, so we can calculate the state gamma 3, which is applying the oracle to the states. Let me check something really quickly. Yeah, so we will apply the oracle, and when we do that, we have 1 over square root 2 to the power n, and then it's minus 1 to the power of, okay, should be within the sum. So I will write the sum first. Sum x 0, 1 to the power of n minus 1 to the power f of x state x, and it should be tensored with state minus, but from now on we will focus only on this part of the state, because after the oracle we stop to care about the last qubit, which is in the minus state. So now what we want to do, so let's rewrite it. So it will be a psi 3 0, and there will be a slight change. So let's write it. And actually, instead of writing f of x, we can write that it's x times s, because we know that this function, the oracle function in the case of the Bernstein-Vazirani problem is expressed in this way. And now we can apply the last layer of Hadamard gates, and that's when the things will become to be interesting. So we are applying Hadamard gates only to these top qubits. So and we will be using this this formula that is in here. So it's 1 over square root 2 to the power of n, sum x 0, 1 to the power of n minus 1x times s, and we are applying Hadamard to this x gate, so just I will rewrite the formula that is visible here. So it's 1 over square root 2 to the power of n sum z in 0, 1 to the power of 1 n minus 1 x times z, and the state z in here. We can write it in a simple way, so it's 1. So we can simplify this parameters, so it's 1 over 2 to the power of n, and then we can have like two sums. They will be, so we are just writing, so there are two sums, but we are writing it as one to have a compact form, and it will be minus 1 to the power x times s plus x times z. And what I will write here will be the claim that we will try to prove in the next step. And the claim is that, okay, I will write another equals sign here, but because I don't have a place on the left-hand side, and I will write that this state is with 100% probability, so with the secret key we are looking for. So now it's time for me to write a justification. Why is that? So let's choose a particular z. So for a particular, and we will observe the amplitude for a particular z. So we are choosing some z. For a particular z, the amplitude is, so we will have only one sum instead of two here, because there is a sum over x and a sum over z, so it will be 1 over 2 to the power of 9 of n, sorry, x belongs to 0, 1, okay, minus 1 x times s plus x times z. And in here I would need to I would like to do some trick that will enable us to calculate the output. So the thing is, so let's take a look at minus 1 to the power of something. And so we want to calculate minus 1 to the power x times s plus x times z. In general, like when we have minus 1, it can be to the even power. So when the power is even, then we have 1, and when the power is odd, it will be minus 1. So that's the things we want to have, and it won't change much in the behavior of this so if we have this minus 1 to the power of something, the behavior will be the same if I wrote it this way. So if instead of just addition, it will be addition modulo 2. So still minus 1 to the even power will be 1, and to the odd will be minus 1. But this trick will it enables us to write this power as x times s XOR z. And we, so the thing is that if if we write it this way, I didn't define what this operation is. So this XOR on two strings is it will just produce another string that consists of S1 XOR Z1. The second element will be S2 XOR Z2, etc. So this XOR operation on strings, it will be useful in the next quantum algorithm. So the Simon's algorithm, but that's another thing. So yeah, we know the definition of this this XOR on strings, and if this XOR has the value all zeros, so no, we can't write like it's not equal to that. So if we assume that string S is the same as string Z, then S XOR Z will equal to 0. So it makes sense because if all the entries are the same, the value of the XOR is 0. And then when we and if we calculate, so let's assume that it actually is true. So S and 0 are the same. So that was explanation there. So if they are the same, this will be -1 to the power of 0 actually, because x multiplied by the vector 0, 0, 0 is x1 times 0 plus x2 times 0 plus xn times 0, which is 0. And in that case, the function, maybe I shouldn't write equal to. So we wrote that the state in here is S, and why is that? Because in this case, if S is Z, then the probability is 1/2 to the power of n, sum over all possible bit strings. It will be -1 to the power of 0, which is actually 2 to the power of n. This sum is to the power of n. We divide it by 2 to the power of n because that's the coefficient in here. And 2 to the power of n divided by 2 to the power of n is 1. That's the amplitude for like some particular z. And we assume that this z is equal to S. And we got the probability equal to 1. So it means that it's only like the only possible outcome of this circuit is actually the secret string S. Like there are many things in this explanation to get, but in general, the very nice thing about this algorithm is that the output is the secret string. And there is some type of different explanation why is that in this notebook. So if somebody is not really keen on this explanation, they can read what is explained in the notebook. And oh yeah, I didn't ask, do you have any questions regarding that explanation? Okay, I will check chat. Okay, so there are no questions as of now. So we've seen the explanation of the algorithm, and now it's time for you to do the task number 3. So you're given an oracle function. It's the external one that constructs a 6-qubit oracle circuit. So the secret string has length of 5. And you need to just write the circuit in the form that is presented here. So I think you can have like 8 minutes for that. I can see that the majority of people have finished, so let's then do this task together. So the first thing is we need to create a quantum circuit with n+1 qubits. N is for the data qubit and the +1 is for the target qubit. Then we need to apply the X gate. So we apply X gate to the last qubit. Last qubit is the N, not the n+1 because we are starting from 0. Then there is this Adamart transfer applied to all qubits. Then we are adding the oracle. So we are using circuit compose. This compose function was used 3 times so far. So we are adding this Bernstein-Vazirani oracle to the circuit. Then at the end, we should apply the Adamart gates to the data qubits, not to the target qubit, but this won't change the result. So that's what we're doing here. And then we are measure the first n qubits. So in here, we are measuring first 4 qubits because in the range, the last number will not be included, and we can see that we are not measuring the last qubit. Between the barriers, we have some oracle encoding the string. I think the yeah, and the output is from this, it will be 0, 1, 0, 1, 1, which is the secret key and what can be seen. So the first one is 0 and we don't have a C note here. Second one is 1 because like we need to read it backwards. So this is 0. Second one is 1 and we have a C note here. The third one is 0. We don't have any C naught starting from qubit 2. Then we have 2 ones on the last qubit. So then we have the C naught gates. So as we can see, the secret key is the oracle for secret key is implemented with C naughts. So now there's the quick last task for today. Task number 4. So we are given the secret key 0110 and you need to implement the function that returns an oracle for this function. Yeah, so you can work on it from now on and you will have around 5 minutes. I can see that most of you have finished by now. So let's quickly see what's the correct solution. So yeah, let's paste it in here. Okay, we're not going to, maybe we can see that. I will print it. Okay, so we see that the secret key was 0110. So if there is so on the qubit where there is 1, we should place a C0. So we place the C0 on the second and third qubits, and that's the whole oracle. So the qubit is the qubit number taken from the secret key is the control qubit, and target is of course always the last qubit. That is the target qubit. Do you have any questions regarding task number 4? I'm checking chat. I can't see any. So now I would like to talk for a second about what we've learned today. So we have seen 2 algorithms, maybe like, okay, let's count it as 3. So Deutsch-Josa and Bernstein-Vazirani. There is a typo here. So in the Deutsch problem, we were mapping a single binary value as input to a single binary output, binary value as output. In Deutsch-Josa, it was an n-bit binary input, and the output was 1 bit. So in this problem, we were considering the question: is the function constant or balanced? And then the oracle that was this mysterious function was encoding this property, whether this function is balanced or constant. In the Bernstein-Vazirani problem, the input is an n-bit string, and the output is either 0 or 1. And what we were doing was trying to guess a secret string S, and the secret string S it was used in the oracle function, and the oracle function was defined as multiplying some input string by this secret string S, and then just calculating what's the output. It should be xn times Sn modulo 2. And there is the third problem. We won't talk about this problem today, but this problem is defined as follows. We are given a function f, and it's from n-bit strings to n-bit binary strings to n-bit binary strings. We know that this function has a special property that it should be 2-to-1 function. So it means that 2 inputs have the same output. And this property that 2 inputs have the same output is so we get this property, and the inputs are related. So when we have some input x, another input that will have the same output as x is x XORed with another string s, and this another string s is the secret key s, and this x XOR s is defined as follows. We've seen it today. So x is an n-bit string, and s is also an n-bit string. So the XOR is like we need to XOR take the value of XOR of the first par x1 s1, second par x2 s2, and for all the other also. And we oh, sorry, something happened to my browser. Okay. So there is this notebook, A06. I can't scroll it. Maybe I can now. Yes. Sorry, it froze for a second. But I will just sorry for the problems with the browser. Oh. But there is a very nice example in here. Okay, give me a second, please. I will try to find a solution around that because my browser is doing weird things now.
I think your microphone is muted.
Oh, thank you. So no, I wasn't saying much, but yeah. So all I told you was that we will try to see how this secret key works in the Simon's problem. So first of all, we can calculate the value for like some arbitrary input. So those are inputs and those are outputs. So we know inputs and outputs, and the output for 0, 0, 1 is 0, 1, 0, and the output for 001 XORed with secret key. Now we are privileged because we know what the secret key is, but usually we don't know that. We want to find this secret key. Is the same as function. So we are XORing the appropriate bits together. 0 XOR 1 is 1, 0 XOR 0 is 0, and 1 XOR 1 is 0. So let me take it here. And now we can see that it is also equal to 0, 1, 0, because we see the values that are printed in red. So the value for this 0, 0, 1 is the same as value for 1, 0, 0. And yeah, the value for this green option showed in here for 0, 1, 0 is 0, 0, 1. And for 0, 1, 0 XORed with a secret key, which is 101, which is f of this will be 1, 1, 1 is equal to 0, 0, 1. So they're equal. So basically the problem is to find this secret key. And in here, you have a notebook that explained like what's the problem, how to solve this, how to solve it using a classical approach. And after there is a quantum solution with an oracle. This oracle looks a little bit different than the oracles we've seen previously. And the algorithm is analyzed in here. So the thing is that we've covered only the Deutsch and Bernstein-Vazirani. So the homework assignment, which will be the quiz that you need to pass in order to get a certificate, will only be about these two topics. And this third topic related to Simon's algorithm, there is a coding assignment, but it's only for the people who want to do this assignment. It's not obligatory. That's all from my side today. Do you have any questions? I can't see or hear any. So thank you very much for today. I think we'll finish a bit earlier, and let's see each other next Saturday at 3 p.m.
Great. Thank you, Stena. Thanks for this great lecture. I will now stop recording.